Today I'm going to talk to you about the properties of the angular momentum operator in quantum mechanics. In particular, we'll talk about the commutator relations and the eigenvalues. Next time we'll talk about eigenfunctions. In classical mechanics, you saw defined as angular momentum equals r cross p. That's still true. If a particle is moving, it has a linear momentum p, and it has a vector that defines where it is relative to some origin. So the cross product is still the angular momentum about that origin. So we have two kinds of angular momentum in quantum mechanics. There's orbital angular momentum, which is that. So L, I'm going to write it this way. It's a vector, so it gets a vector sign. It's an operator, so it gets the caret. And that equals r vector cross p vector. I'm going to work this out as if we were in classical mechanics. So the r vector is written as x I hat. And you'll notice I have the carets over the I, J, and k. Those are different carets. Those mean unit vector. Confusing notation perhaps. I normally use the carets to indicate operator, but we have to have a little bit of classical mechanical notation here. Use them on the unit vectors as well. And you can work out that cross product. There's another kind of angular momentum in quantum mechanics, and that's the spin angular momentum. And I can't give you such a nice, neat description of it in terms of an r and a p crossed with each other. It's far more abstract. It has no classical mechanical analog, other than maybe to think about a planet spinning on its axis and the planet's made of charge. It's not quite accurate, but that's how you might visualize it. I don't have as straightforward a way to model it as r cross p. However, the orbital and spin angular momentum do a lot of the same things, and they function mathematically in very similar ways as operators. But they're not even close to the same thing, meaning that they don't have common eigenfunctions, so they don't commute. However, they do commute. That is, since they have absolutely nothing to do with each other, it doesn't matter if you operate with L first or S first on a good eigenfunction, say of the hydrogen atom, for example. It won't matter because that eigenfunction is separated into spin and angular momentum parts. Keep that in mind, that order between L and S isn't going to matter for the physics of the hydrogen atom. So we can generalize to total angular momentum, and it's called J, and it's a combination of orbital angular momentum and spin angular momentum. And that's what we're going to use for the rest of today. Everything that we do for J works individually for L and individually for S. So that's why I'm using J, because it applies to both. So when we get to spin, everything we cover today is still going to be valid. You just use S instead of J. And when we deal with angular momentum eigenvalues, say of the hydrogen atom, everything we do today is perfectly valid. You just use L instead of J. Now the vector components of L, S, and J have certain commutation relations called the cyclic commutators. Let me write them down. Do you see why they're called cyclic commutators? There's a pattern from Jx to Jy to give you Jz, and then Jy to Jz to give you Jx, and Jz to Jx to give you Jy. It looks a lot like cross products of unit vectors. There's a consequence of this set of statements. In classical mechanics, you're unlikely to come to this conclusion, that when you look at the commutation of x and y components of angular momentum, you get the z component. That is really a quantum mechanical thing. So the consequence of these cyclic commutators is that I h bar j equals j vector cross j vector, which on the surface is absurd. A vector crossed with itself is supposed to give 0. Let's look at how this works out when the components of j do not commute. So if j cross j is I h bar j, let's expand out j cross j. So j can be written in its component forms using the unit vectors I hat, j hat, k hat. And I'll dispense with the hats on the j's because it's just too many hats. And now we need to evaluate this triad. Now normally you would set up a determinant with I hat, j hat, k hat across the top, and then jx, jy, jz on the second row, and jx, jy, jz on the third row, and evaluate that determinant. I'm going to skip the determinant, and I'm going to actually evaluate this product one term at a time. So if you look at ij sub x, cross ij sub x, then cross ij sub y, then cross kj sub z, and then jj sub y, cross ij sub x, and so on. 9 terms emerge from this triplet cross product, and you can immediately rule out 3 of them, these 3 diagonal terms, because I hat cross I hat for sure is 0, and j sub x and j sub x commutes with itself. I would also make the observation that, say, for example, these 2 don't cancel. In classical mechanics, you would normally say they cancel. I hat cross j hat is k hat, j hat cross I hat is minus k hat, and these 2 terms would simply cancel. But the j sub x and j sub y don't commute. You can't dispose of these 2 terms on the grounds of them adding to 0, so we have to keep them. So this one is k hat, jx, jy, and so on. And none of them add to 0. But what do they add to? Group them into their unit vectors again, and look at each one of these parentheses. What's in each one of these parentheses but a commutator? So j cross j is I hat, j hat, and k hat times these 3 commutators. And these 3 commutators were defined in those cyclic commutator relations. You can take a look at them. Factor out the IH bar, and you simply have the j vector again. So that's why j cross j is not 0 as you might expect, because the components don't commute. It's actually IH bar j. Everything we just did with j applies to L as well as S. Now let's look at what happens if any 2 of these were able to commute. Then the commutator would be 0, and let's look at the consequence. The proof brings us back to the generalized uncertainty principle. The commutator of 2 operators is I times the commutator of a third operator, where A, B, and C are all Hermitian. In this case, you have the commutator of j sub x and j sub y is I h bar j sub z. So that's the C in that statement. But if j sub x and j sub y have the same eigenfunctions, then the commutator j sub x and j sub y also has to be 0. Therefore, j sub z is 0. And consequently, the uncertainty of j sub z is 0, because it's exactly 0, so that's with no uncertainty. The generalized uncertainty principle can be invoked. The uncertainty of j sub x times the uncertainty of j sub y has to be greater than or equal to h bar over 2 times the magnitude of the expectation value of j sub z. Therefore, the uncertainties of j sub x and j sub y are also 0. Okay, you could say, well, the uncertainty of one of them is, but there's no way to distinguish between them in the kind of symmetry that we're dealing with, so they must both be 0. And so it follows then that j sub x has no expectation value, nor does j sub y. There is no angular momentum. I'll put it this way. I'll do j squared, should have our hats. That's the commonly used angular momentum operator, the square of it. But that is 0 plus 0 plus 0. It has no expectation value. Therefore, 2 components of the angular momentum cannot have simultaneous eigenfunctions. Their commutators cannot be 0. However, each component of the angular momentum will commute with j squared, meaning that j sub x and j squared have common eigenfunctions, j sub y and j squared have common eigenfunctions, and this is what we're going to use. J sub z and j squared have common eigenfunctions. Let's see this. All right, the commutator. And you can repeat the whole thing with j sub x and with j sub y. And of course, the whole thing is true individually with L, orbital angular momentum, and S, spin angular momentum. So I expand the commutator by taking j squared, which is magnitude, It's j sub x squared plus j sub y squared plus all of them. The third term is definitely 0 because every operator commutes with powers of itself, which just leaves these first two to contend with, and I'm going to expand those commutators. Looking at the first two of these four terms, the squareds mean to apply the operator twice. So this is actually j sub z, j sub x followed by j sub x, and this is j sub x followed by j sub x followed by j sub z. And you might be wondering why do that. I'm going to add two terms that cancel. I'm going to add, and I'm going to add minus the same thing. And that's rewriting the first two terms. And then you have to do the same for the j sub y, j sub z terms. We'll just look at these four because the first two terms in this line do exactly the same thing that the second two terms do. There's a commutator in here if you look at the first and the fourth term here. I can have a common j sub x at the end of each term. Do you see how that's the first and the fourth term? And the second and third term can have the same thing done to them. You have a j sub x in front, and then you have this commutator between jz and jx, and then the jy, jz terms. Applying the cyclic commutators to these four commutators, we can write down what the expectation value would be, fix a little mistake there, jz commuting with jx gives you j sub y, so the expectation value is going to be I h bar jy expectation value, jx expectation value. Because jx and jy do not have common eigenfunctions, the expectation value of the product jy, jx needs to use separate eigenfunctions for y and eigenfunctions for x. And that breaks apart into two different integrals. Just in case you're wondering why, it's obvious that I can say the expectation value of this thing is the expectation value of each one of these operators separately. I'm going to erase this now. Plus I h bar expectation value of j sub x. Now this one, commutator jz with jy is minus I h bar jx. And commutator jz with jy is minus jx. Now these are just numbers, and numbers commute. So this adds up to 0. So j squared and j sub z commute, and they have simultaneous eigenfunctions. The same holds true for j sub x and j sub y, but we're going to hang on to j sub z and use that. So if j squared and j sub z have simultaneous eigenfunctions, then it would follow that j sub z operating on some eigenfunction, which I'm going to just call m, is an eigenvalue times phi sub m. In quantum mechanics, angular momentum is always a factor of h bar because h bar is dimensions of angular momentum. So I'm going to say this, that j sub z operating on its eigenfunction is some eigenvalue, which is a number m times h bar. I'll do the same for j squared, where j times j plus 1 is some constant, and angular momentum squared goes as h bar squared always. What we're going to find is that, and I'm just giving a preview here, j can be 0, 1/2, 1, 3/2, 2, ... m can range from minus j plus 1, ... up to j. But that's a preview. We have to show that to ourselves. Let's prove these eigenvalues. And to do that, we need to invoke an operator. We'll call it J sub plus. J sub plus is J sub x plus I times J sub y. And in case you're wondering, we could imagine another operator called J sub minus, which is J sub x minus I J sub y. This should look familiar to you from our treatment of the harmonic oscillator, where we first used ladder operators. You can confirm this particular commutator between J sub z and J plus is H bar J plus. I'm leaving that as an exercise to you. We're going to use this commutator. Let's apply it to one of these common eigenfunctions. So using the rule of this commutator, the commutator is H bar J plus on phi sub m. This can be rewritten as just H bar m times phi sub m. And rearrange this line right here to give you this. Bring the second term over to the right-hand side. So it would appear that this product of the J plus operator on phi sub m is an eigenfunction of J sub z with eigenvalue m plus 1 h bar. But here's a little bit of an issue. Eigenvalue m plus 1 h bar also goes along with a different eigenfunction of J sub z. It's also true that J sub z on phi sub m plus 1, the next eigenstate, is m plus 1 h bar, just by virtue of the way we have defined the effect of J sub z on phi sub m. But J sub z cannot be degenerate because atomic states are bound in the z direction. And in a one-dimensional bound state, you cannot have degeneracy. So in the z direction, we can't have degeneracy. So two eigenfunctions cannot have this same eigenvalue unless they're the same eigenfunction, leading me to the conclusion then that this J plus on phi sub m must be the same thing as phi sub m plus 1, at least within a multiplicative constant. And likewise, you can show that J minus on phi sub m minus 1, at least within a multiplicative constant. So J plus is a raising operator, and m progresses then in unit steps. So let's find a relationship between m and j. We had the commutator, J sub z on J squared is 0. Therefore, it's also going to follow that J squared on phi sub m is an eigenvalue times phi sub m, right? Because Jz and J squared need to have common eigenfunctions. Let's call this eigenvalue, for lack of a better name, h bar squared times another constant, k squared. You know, the eigenvalue when Jz was the operator, we called h bar times m. Oops. So when J squared is operating on phi sub m, we'll call the eigenvalue h bar squared k squared. If I ask what's the expectation value of J squared, it's the expectation value of its component squared, because you dot a vector with itself, you just get the sum of the components squared. And then that's h bar squared k squared, because that's what I just set up here. But we already have that J sub z has an expectation value of h bar m, so the expectation value of J sub z squared is h bar squared m squared. So at least something seems evident. What seems evident is that whatever k is greater than m squared. Whatever k squared is greater than m squared. Or rather, k is greater than m, but you should really put absolute value signs on there because maybe it's negative. So it would seem then that there is a maximum value that m can have. M cannot be larger than k. it's equal when the expectation values of jx and jy are 0. Otherwise, k is greater than m. So it would follow then that there is a maximum value that m can have, and it's k. And since the raising operator j plus operating on the eigenfunction with that maximum possible value is 0, because any attempts to raise the level above the max will result in 0. And likewise, there's the lowering operator I mentioned. If you apply that to the smallest value that m could have, which apparently is minus k, because k squared is greater than or equal to m squared, you will get 0, because any attempt to lower the level beyond that is going to have to give 0, because m cannot exceed k. There's no states available past that point. Now we need something in terms of j that actually makes j plus and minus happen. Let's evaluate the product of these two operators. And really, you don't have products of operators, you have one operator followed by the next operator. And remember, these components of j do not commute. Or I is the square root of minus 1. It's not a unit vector. Recognize these middle two terms as a commutator, and recognize jx squared plus jy squared as j squared minus j sub z squared. And what's the commutator? But which is then j squared minus j sub z squared plus I, and look at the cyclic commutators. Commutator of jy with jx is minus I h bar jz. Okay, that is what you get with j plus followed by j minus. So we have j squared equals j plus j minus plus j sub z squared minus h bar j sub z. Likewise, if you start right here with j minus j plus, you can come up with j squared equals j minus j plus. Okay, now then we're ready to apply the j squared operator to those same eigenfunctions that are shared with the j sub z operator. Let's look at what happens when it is applied to the same eigenfunction j sub z uses with the eigenvalue m max. First thing I would note is that this term is 0, because as soon as you apply the raising operator to the state with eigenvalue m max, you don't get a state anymore because you can't have a higher eigenvalue. So that term is 0. This j squared phi sub n m max, we said we're just going to nickname it, it's h bar squared k squared on phi sub m max. So equals 0. jz squared on phi sub m max is h bar m sub max, and you get it twice because you apply jz twice to that eigenfunction. Finally, j sub z on phi sub m max gives you h bar m max. These are all numbers, so the eigenfunction can now be cancelled because numbers do nothing to an eigenfunction. Then we're left with the statement that k squared equals m max times m max plus 1. If you went ahead and applied this other j squared operator that contains j plus j minus and do the same exercise here, you would find k squared is not m max but m min, the minimum. minus 1. Remember, m minimum comes about because k squared is greater than or equal to m squared. Therefore, there's a maximum value for m and there's a minimum value for m, which is equal and opposite. And this can only be true if that's the case. If you were to subtract these, you would get, this can only be true if m min is equal and opposite to m max. So the sequence of m's is symmetric about 0. M goes from minus m max to m max. So let's rename something here. I'm going to rename m max j, so that I can say the expectation value of j squared is not h bar squared k squared, but since k equals m max, and the nickname that we came up with for k was j times j plus 1, we can write the expectation value of j squared as h bar squared j times j plus 1. So the number m, which when multiplied by h bar gives you the eigenvalue of the j sub z operator, can range from minus j plus 1, j minus 1, j. It's symmetric about 0. It corresponds to either orbital or spin angular momentum or the two added together. So when j is an integer, it can be orbital or spin. J can be a half integer, and when that's the case, it only corresponds to spin. And I would just summarize it as we have an angular momentum operator, j squared, that's the square of the angular momentum, and it can be L, S, or the sum L plus S. And it can operate on its eigenfunction, giving you an eigenvalue of h bar squared times the quantum number j times j plus 1, where j can be any half integer. However, if it's a half integer, it only corresponds to spin. If it's a full integer, it can correspond to spin or orbital. And j sub z operator on the same eigenfunctions. They're simultaneous eigenfunctions. And m runs from minus j all the way up to plus j. And this is true for any eigenfunction shared by j squared and j sub z. That's our grand conclusion here. This is the thing you need to take with you. And just remember, it can be for j, which is L plus S, or it can be for L by itself, or it can be for S by itself. Okay, next time we'll talk about these eigenfunctions phi sub m.